All right, welcome everybody. It is my great pleasure to introduce our first water lecture speaker this semester, Stefano Gonella, who is currently an associate professor and the only aerospace engineer in our department. As a reminder for everybody, this lecture is a part of the promotion process to the rank of professor. Stefano earned his BS degree at Politecnico di Torino in Italy in 2003, followed by the master's degree at Georgia Tech in 2005 and a PhD degree only 2 years later at the same institution. After graduating from Georgia Tech, Stefano spent 3 years as a postdoc at Northwestern University and joined our department in 2010. Stefano received the NSF Career Award in 2015. Research-wise, Stefano investigates waves in engineered, or if you will, microstructured materials that give rise to a wide range of exciting physical phenomena with direct applications to wave manipulation and control. In terms of civil engineering applications, you can think of vibration isolation and vibration energy harvesting for sensing purposes as examples. In particular, Stefano's today's lecture will focus on the wave manipulation near edges and interfaces of such architected materials. With this, I would like to turn the mic to Stefano, and I will ask you to save all your questions for after the lecture. By default, your output video and audio should be disabled until then. Stefano, the floor is yours.
Thank you, Boyan, for the introduction, and good morning to everybody. Thanks for joining. A little disclaimer before we start, as I mentioned in the preamble already, to some of you who were connected early, I have been battling a vocal cord inflammation for the past several days. So I think I'll be able to pull through, but I apologize in advance if that happens, ends up affecting parts of the presentation, the speaking, maybe the effervescence of the delivery. So today, I will talk about a piece of research in metamaterials engineering, specifically an area of metamaterials that has blossomed in the past few years, and thanks to the injection of new ideas and concepts and notions that originated in part in the quantum physics community and in part in the mathematical topology community. So we are really at the intersection of these disciplines. The work today is predominantly the work, I would say almost exclusively the work of a former postdoc in the group, Ji-Hong Ma, who is now an assistant professor at the University of Vermont. In fact, she's just starting her group at Vermont this month. And this is work done in collaboration with a fantastic group of theoretical physicists at the University of Michigan, namely Kai Sun and Xiaoming Mao, and their former postdoc Bi Zhu, who is currently at Georgia Tech. The talk is about metamaterials, so I thought it would be nice to start with the sort of definition of a metamaterial. A metamaterial is essentially an architected material, so synthetic, man-made material that consists of a network of individual parts or building blocks. Now, the building blocks taken in isolation as individual units are fairly conventional elements, rods, beams, plates, shells. But because they are arranged in space and because of how they are connected to each other, they end up yielding global properties at the system level that transcend those of the individual parts. And typically, these properties are quite unconventional and go beyond what is typically achievable in natural materials. And this is, I guess, encoded in this prefix meta in the name. So to exemplify what I just said, think, for example, a simple system like a rod, a homogeneous rod. We know everything about it. This is as simple as a mechanical system as we can think. Then we can also think about a little plate, also homogeneous, so also fairly simple and well known. Then what I can do is I can put them together, and I can form this unit, which is already a little bit more complex. It's sort of like a pillar, right, or a stub on a platelet or a pedestal, or on a substrate. And then what I can do is I can somehow repeat this in space, and I can do that in a way such that the height of the pillar is the same everywhere. So I end up with a periodic structure that features a spatial order, or I can modulate the height of these pillars. So I end up with a spatially disordered or aperiodic system. Either way, I can talk about a metamaterial. And now all of a sudden the geometry is quite a bit more complex, and this complexity in the geometry produces an equivalent complexity in the mechanical behavior that these systems feature. And by the way, this system is what we would call a stub plate. And here are a few examples from the literature of stub plates that have been studied for a bunch of applications, ranging across scales. So this would be a tabletop experiment. This is an application at the microstructure. This is, at the microscale. This would be at the end of the spectrum on one end, a nanoscale application, when in this case the pillars are actually not even manufactured but grown from a substrate. And this is at the other end of the spectrum. This is interesting work by Colombian co-workers that studied the behavior of forests of trees and kind of postulated and demonstrated that they can actually potentially work as seismic metamaterials that can interact with the seismic waves and manipulate them. And finally, this is a little prototype that we built in the lab a few years back with former student Paolo Celli. In this case, the plate was just a piece of Lego board, and the pillars were these little Lego bricks, these little stems. In this case, you see that the conical tip was actually adjustable in height, so that we could implement and vary pretty much on demand the pattern of heights, therefore transitioning from uniform to periodic to aperiodic arrangement. So this would be something that we would call a tunable or adjustable metamaterial. Another concept that is kind of important, somehow related, is the concept of a phononic crystal. A phononic crystal is essentially a structural material that mimics the periodicity of natural crystals, and therefore adopts some of the behavior that is observed in natural crystals. And here are two examples. This would be like a periodic arrangement of metal rods in air for the control of sound waves. And this would be a periodic arrangement of holes drilled into a slab of material. And this would be for the control of elastic waves that propagate in the slab. Now, these phononic crystals are known to feature a variety of very exotic wave manipulation capabilities. And here I just list a few, and I boxed the three that are perhaps the most classical and well-known ones, which, however, are the ones that we really need to focus on for this presentation: phononic bandgaps, wave directionality, and waveguiding. So I think I would spend some time to introduce these three concepts one by one. So in order to understand what a phononic bandgap is, we need to say a few things about how we study the frequency response of these periodic structures. And the way we do that is by means of what is called a unit cell analysis or block analysis. And I'm going to illustrate this with this example. This is a chiral lattice that I studied a few years back, even before joining Minnesota. It's obtained from the tessellation in space in 2D of this unit cell, which is enclosed in the yellow circle. Now, the starting point of the analysis is a model of the unit cell. For example, I can build a finite element model of the unit cell, which means that I have in my hands a stiffness matrix and a mass matrix for the cell. Then I need to impose some boundary conditions. And in this case, the boundary conditions that I need are a special kind of boundary conditions known as block conditions, which account for the fact that this cell is in contact with its neighbors and is actually part of an infinite domain. Now, the application of these boundary conditions yields an eigenvalue problem. And in the eigenvalue problem, we have the frequency of wave propagation, omega, and then we have these two parameters, K1 and K2. Now, K1 and K2 are the two components in the plane of the lattice of the so-called wave vector. Now, the wave vector is a vector that lives in the plane of the lattice structure. Its direction indicates the direction of the propagation of a plane wave that we intend to study in the lattice domain. And its amplitude is inversely proportional to the wavelength of the wave. So this eigenvalue problem puts in relation the frequency and the wave vector. And in fact, the solution of it gives me this set of solutions, omega, functions of K1 and K2. And these solutions, these eigenvalues are called are surfaces in the wave vector plane, and they are called the dispersion surfaces. And altogether, they form the so-called dispersion relation of the lattice, which is a sort of map that contains all the information about the mechanical behavior of this periodic system. Now, the most effective way to graphically depict the dispersion relation is in the form of a Venn diagram, which is this relatively complicated object that you see here, which I will try to explain for those of you who don't work in the area. So here on this axis, I have the frequency, perhaps properly normalized by some normalizing factor. And you can forget about all these letters, strange letters here on this axis. Essentially, on this axis, I sweep the wave vector. So I consider wave vectors that have different magnitudes as well as different directions in space in a way that somehow accounts for all the possible interesting directions and magnitudes of wave propagation. All these curves that you see here are families of eigenvalues. They are wave modes. And the two lowest ones, which actually start from the origin, so that have that start at zero frequency, we call them acoustic modes, and then all the others we typically refer to as optical modes. And so they represent families of wave modes. Now, for each eigenvalue, I have a corresponding eigenvector, and the eigenvector represents a mode shape of the unit cell, so a deformation mechanisms that the unit cell can experience that corresponds to that frequency, to that eigenvalue. So how do I navigate this plot? Well, I say that, for example, if I excite a lattice at a frequency that is right here, I will excite all the different wave modes that live at that frequency. And for example, this mode right here will involve the generation of a wave that will propagate with a wavelength whose characteristics I will read on this axis. And when this wave propagates through the domain and it impinges on a unit cell, it activates a deformation mechanism for the unit cell, which is captured by the corresponding mode shape or eigenvector. Now, the interesting thing here is that you see that there are some frequency intervals where I do not have any real eigenvalues. So I do not have any branches of this dispersion relation. And these are called the bandgaps or phononic bandgaps. Essentially, they are frequency intervals where wave propagation is forbidden, or to be more precise, where wave propagation is evanescent. In other words, if I had to excite a lattice at a frequency that falls inside a bandgap, the waves will not propagate in the far field, but rather they would attenuate very sharply in the neighborhood, immediately in the neighborhood of the source. So this is the description of the mechanics of a periodic structure that a solid-state physicist would also potentially provide. But there is another point of view, and the other point of view that is interesting for us is the point of view of the vibration engineer. A vibration engineer would say, let's consider a finite lattice, a finite domain with a finite number of unit cells. Let's apply, let's say at one edge, a harmonic excitation with a frequency that we control. And let's see what is the output that is transmitted to the other end. So I could, for example, compute and plot the transmissibility, so some kind of metric of output over input, as a function of the frequency. And I would obtain this frequency response that is shown here, where I see I have all the different peaks that are the different resonances of the vibrating system. But you notice that there are two frequency intervals where the response is severely attenuated. So I have dips in the frequency response. And these intervals happen to correlate very precisely with the band gaps that we have studied through unit cell analysis. So you see that I have a unit cell description and a finite lattice description that's kind of harmoniously shake hands. Another interesting phenomenon that these periodic structures feature is known as directionality or directivity. Again, let's use this example as our benchmark example. I can build what we call group velocity contour plots. So essentially, these are polar plots where I plot the magnitude of the velocity of a wave as a function of the direction of propagation in the plane, as a function of an angle. And I see something quite interesting, that at low frequencies, the behavior is so-called isotropic. In other words, the velocity is actually the speed, the velocity of the wave is actually the same in all possible directions of wave propagation. But for the same structure, if I just excited a higher frequency, then all of a sudden I start seeing these lobes, and then eventually these loops in these patterns, as opposed to these circular patterns, which means that I start activating some preferred pathways, some preferred avenues along the waves propagate faster. So some channels along I would like to direct my energy. And so I have this anisotropic directional behavior, which is frequency dependent. And in fact, I can also consider a finite lattice, perform, for example, a simulation where I excite a point in the middle of the domain, and then I let the wave propagate, and then I take a snapshot of the wave field. And here I have the color is proportional to the accumulated energy at a given time instant, and I see that in fact the energy has propagated predominantly along these preferred directions, which actually correlate to these particular loops in this representation for an excitation at that frequency. One cool thing that one can do with bandgaps is waveguiding. Waveguiding has to do with the ability to channel the energy along an arbitrary path in the domain. So here I'm using this example from the literature. This is one of the earliest, if not the earliest, demonstration of waveguiding in a phononic crystal by Khalif and co-worker. So imagine we have here a phononic crystal which has a bandgap. And we come in with a plane wave from the left, and the frequency of that plane wave falls inside the bandgap. And here I have defected the crystal, somehow relaxing the periodicity along this path. Now, of course, the wave cannot propagate into the bulk because of bandgap condition, but it can propagate along this coordinate because bandgap conditions are actually removed in here. So I can channel the energy along this arbitrary path, and then the energy is released to the right of the dome. And in fact, we performed like a few of our own demonstrations in our lab, again, using the Lego platform that I mentioned earlier, that was quite powerful for us to demonstrate a number of concepts in phononics. So here you see a plate, a Lego board with a periodic architecture of stubs. Again, these Lego bricks, which are arranged in this fashion. And you see that the periodicity is relaxed along this path. And then we scan the back of this plate using a laser vibrometer. And these are two results of two scans, one at lower frequencies and one at higher frequencies. And both frequencies happen to fall inside a bandgap for this configuration. And you see that indeed the energy is channeled along the waveguide that is architected. Okay, so now, one of the most interesting flows of ideas that have really changed the landscape of metamaterials research in recent years have come, like I mentioned at the beginning of the presentation, from these injections of notions of topology. Now, topology is essentially the study of the properties of objects or shapes that are preserved under continuous deformations. And by continuous deformation, I mean the following things: stretching, twisting, bending, crumpling, but not tearing or gluing. So essentially everything that does not involve piercing new holes in solid or stitching parts together. So topology essentially enables a classification of solids. For example, I can say that the cow and the sphere belong to the same topological class because I can deform continuously one into the other. So there is a certain topological index that I can come up with that captures this topological family. Similarly, the mug can be continuously deformed into a donut. So mug and donut would also fall into a different topological class, but the same topological class among themselves. Okay. So what does this have to do with wave propagation? Well, the connection is somehow subtle. We need to remember that when we deal with a propagating wave, we often characterize the wave in terms of its frequency and wave number or wave vector components. So essentially in terms of its Fourier characteristics. So we provide a representation of the wave in Fourier space. And in fact, the wave can be described by geometric objects that live in Fourier space. For example, those dispersion surfaces that I mentioned earlier that come from the solution of the eigenvalue problem for the unit cell are indeed geometric objects that live in the frequency wave number space. Now, nothing prevents us from performing a topological description of this geometric object. And by doing that, we end up obtaining a classification of the different wave phenomena that these geometric objects actually represent. And this is precisely the game that people and physicists have been playing for a few years now. And that has led to the discovery, and first of all, to a different interpretation, even of classical concepts in wave propagation, but also to the discovery of new wave phenomena, which were until recently unknown or understudied, and also the development of new metamaterial architectures that have wave functionalities which were until very recently underexploited. So today I would like to talk to you about two problems that I think fall in this family of topological metamaterials, or topological phononics, if you will. The two problems seem distinct, but I will show you that actually they have a lot in common, both from a methodological standpoint, as well as from the point of view of the phenomena that I am studying. The first one has to do with wave propagation in Maxwell lattices. So let's start with this one. So first of all, I have to introduce what a Maxwell lattice is. And to do that, I have to introduce a sort of taxonomy of lattices based on their coordination number. Now, a little disclaimer, for the time being, our lattices are ideal lattices, meaning they are just a bunch of lattice sites or lattice nodes that are connected by links or bonds. And each lattice site behaves as a perfect hinge. So I have free rotation of the links about this hinge. So all the forces that are exchanged at each hinge are only central forces, and each node only talks to its nearest neighbors. So the coordination number of the lattice is the number of lattice sites that each site is directly connected to. So I can have this situation where the coordination number is less than 2D, and D is simply 2 in 2 dimensions. So this right-hand side would be 4. When Z is less than 4, I talk about under-coordinated lattices. And the typical example is the hexagonal lattice. And under-coordinated lattices are known to be very floppy, very soft. Or to be more precise, they allow a large number of floppy modes. By floppy mode, I mean what in engineering mechanics we more often refer to as a mechanism. So that is a lattice deformation that do not involve any generation of stresses in the bonds. In other words, a lattice deformation that does not cost any energy. Okay. On the other end of the spectrum, I have over-coordinated lattices where Z is greater than 4 in 2D. And the typical example is the triangular lattice, where Z is equal to 6. And everybody has experienced that the triangular lattice is a stiff lattice. And in between, I have so-called Maxwell lattices that are called this way because Maxwell was actually the first who first had some kind of formal intuition of their behavior. And in 2D, a typical example is the kagome lattice, which is shown right here, where each node is connected to 4 neighbors. So essentially, it's a collection of equilateral triangles. Now, for a Maxwell lattice, this business of floppy modes is more complicated. So the existence of floppy modes and the number of floppy modes depend on the specific geometry of the lattice, as well as on the boundary conditions of the problem. For example, I can consider the problem of periodic boundary conditions. Periodic boundary conditions means that I consider infinite lattices. Now, in this case, what we are interested in is the existence or lack thereof of floppy modes in the bulk. So, for example, we can consider a regular kagome lattice, which is shown right here. You see that it's a lattice where the bonds are aligned along these straight directions. And the regular kagome lattice turns out to allow floppy modes. For example, I can have this deformation mechanism, which is shown here, where the equilateral triangles are rotated in this fashion. And as you see, the deformation is only localized in a strip of material and decays away from it. Formally, this can also be captured by performing a unit cell analysis of the lattice. So here, ignore the solid lines, just concentrate on the dashed ones. And you see that I have one wave mode that actually has a piece of the branch right here where my cursor is that lives at 0 frequency. So this 0 frequency, 0 energy mode corresponds to this floppy mode, this deformation mechanism that I shown here in the cartoon. However, a little change in the geometry produces a dramatic change in behavior. For example, look at the twisted kagome lattice, which is simply obtained from this one by initially twisting all the triangles. Well, this one does not have those straight bonds anymore. And actually, the ability to have floppy modes is lifted. If I look at the Venn diagram, I see that I do not have any branch at 0 frequency anymore. But this is the periodic boundary condition is really not the scope of today's presentation. Today, we're interested in open boundary conditions, and that's where things become even more interesting. By open boundary conditions, I mean that I have a finite lattice, so a lattice that has boundaries or edges. Now, the question here becomes, can I have floppy modes at the edges? Now, the existence of some kind of floppiness at the edges of a lattice is really no news. I mean, every lattice has some kind of floppiness at the edges. In fact, any system does, because as you can imagine, in any system, the points that belong to the boundaries are less coordinated than those in the bulk, in the interior. So their mobility is higher. But when it comes to Maxwell lattices, something peculiar happened. So it has been shown by Kane and Lubensky in their seminal 2014 paper that these lattices may have the ability to focus the floppiness, focus the floppy modes on specific edges. Look, for example, at this example straight out of Kane and Lubensky. Here we have a finite lattice, a small chunk with 3 sides. Well, they show that, for example, you can have this side, this edge, that is a rigid edge or a non-floppy edge. So I do not have any floppy modes on this edge, whereas I have 2 floppy modes available on this edge right here. So this one is deemed as the rigid edge, and this one right here is deemed as the floppy edge. And they also introduce a formal way to characterize this polarization, and that is through a polarization vector. The polarization vector, when it is non-zero, it indicates that we have polarization. At the direction of the vector points to the edge that is deemed as the floppy one. So in this particular case, the polarization vector points down, and therefore it deems this edge as the floppy one. Now, the mathematical construction of the polarization vector is not the simplest thing, and so I'm not going to attempt to cover it in this presentation. But I would like to point out a few interesting things about the polarization vector that actually tells us a lot about the physics behind the problem. You see that the polarization vector, the construction of it involves the lattice vector, so the primitive vectors of the unit cell, as well as these quantities right here, these winding numbers Ni, which are actually the topological indices of the problem. And these winding numbers come from the solution of this integral. And if I look at the argument of the integral, of the integrand, I actually have the compatibility matrix of the unit cell. The compatibility matrix of the unit cell contains the so-called strain displacement relations of the unit cell. So in other words, the polarization vector depends on the geometric and kinematic characteristics of the unit cell. Now, this statement sounds perhaps a little bit strange, right? Because what I'm saying here is that this quantity that I can construct starting only from unit cell information actually controls the behavior at the edges of a finite domain. And that is peculiar because the unit cell, as part of an infinite lattice, does not know anything about the existence or about the characteristics of any boundaries. Nevertheless, this polarization vector captures a phenomenon whose manifestation becomes real only when I actually consider a finite lattice that has boundaries. And this is a textbook example of a principle that is one of the underlying principles in topological mechanics, known as the bulk edge correspondence. Precisely the idea that I have a property that is intrinsically a property of the bulk, which, however, controls the manifestation of something at the edges. So in order to bring it to life, I really need to consider a finite domain. So in order to exemplify a little bit what this means in practice, here is a little demonstration with a prototype that I built a few months back. And some of you who walked by my office at the time when we were in the building might remember this object on my desk. So it's a topological lattice, a Maxwell lattice built using these Lego Technic components. Actually, this is a reconfigurable lattice because I can actually reorient the rotation of these links in order to kind of change the properties. But the way it is shown here is actually in polarized, as a polarized behavior. And in fact, you can even see here in this polarized state where essentially these bonds are kind of all aligned. Now, to be precise, this is almost a transition condition where I cannot really formally compute the polarization vector, but for all intents and purposes, qualitatively, we can say that we have a polarization in this direction. So now look at what happens when I try to apply a static force from this edge. You see, I come in with my hand, and when I push, I can indent the solid. In other words, I can indeed exploit the floppiness of this edge and localize deformation. Now look at what happens when I instead push from the other side. You see that I have a rigid behavior, and actually, interestingly enough, with respect to both pushing and pulling as well as sideways activation. So this is like quite a powerful practical demonstration of the asymmetry of behavior between this edge, which is the floppy edge, and this edge, which is the rigid one. So with all this background in mind, we ask ourselves this question. What happens when we go from ideal lattices to realistic lattices? In other words, or structural lattices. In other words, what happens when I replace the ideal hinges that I used to have here at the lattice sites with these ligaments that are essentially these little beams with a certain bending stiffness? So, by the way, this is exactly what happens if I try to manufacture this kind of lattices, for example, using 3D printing, or for example, using some kind of cutting technique. Well, the intuition suggests that I am stiffening the systems so that the whole spectrum of the response should migrate to higher frequencies. So I should actually go from a static behavior to a dynamic behavior. But that brings about some fundamental questions. Number one, can we still talk about floppy edges and non-floppy edges, floppy modes and non-floppy modes? And if so, do these edge modes retain the topological attributes which I just described? And also, if now these floppy edge modes are not static modes anymore, but dynamic modes, so if they migrate to finite frequencies, all of a sudden they are going to coexist with the bulk modes, so modes that propagate in the interior. How am I going to distinguish one from the other? So we try to answer some of these questions through an experimental approach. So we look at the behavior of finite lattices like this one right here. Our experimental prototype is actually a little bit bigger than this, but this is just to give you an idea of the geometry. You see I have a periodic arrangement of unit cells like the one shown here. You even see the mesh of our finite element model. So these are the two primitive vectors, and you see that it consists of an equilateral triangle and an isosceles triangle, which is slightly tilted with respect to the other one. Okay, so it's a unit cell that lacks mirror symmetry. And with this configuration, we have a polarization vector pointing as the arrow shows that actually deems this edge as the floppy edge and this one as the rigid edge. So before looking at the behavior of the edge, we actually try to understand how waves propagate in the bulk, which is more background information for us. So we ran a test like this one. You see here our specimen. This was obtained via water jet cutting, starting from a thin slab or thin sheet of ABS material. So it's a thermoplastic material. And here you see a detail of one unit cell that gives you a sense of the proportions, and you also appreciate the thin ligaments that qualify as hinges. The specimen was placed vertically like this. It was clamped at the two sides, while the top and the bottom were left free. And here I was applying an excitation through a shaker with a stinger. So the force was applied in the plane of the lattice and exerted at this point on the edge. And then I was using a 3D laser vibrometer to scan the surface of the available surface of the lattice and reconstruct experimentally the in-plane motion of the points belonging to the surface, and therefore obtain an experimental map of the wave field. And this is what happens at a certain frequency that should excite a bulk wave, so a wave in the interior. These are 3 consecutive snapshots. So the wave starts from the excitation point, and then it propagates into the bulk. And as you see, it does so in an interesting way. First of all, it's a very directional. So you see that the energy doesn't propagate isotropically, but rather tries to propagate along these 2 specific directions, which actually correlate to with the primitive vector of the lattice. And more importantly, we also have an asymmetry in the response. Right? So the idea is that when we have an asymmetry in the geometry of the unit cell, that is going to induce an asymmetry in the wave field that we observe at the global scale in the lattice. Okay, so now with the behavior of the bulk understood and kind of matching our expectations from our simulations, we can now finally look at the edges, which is really what we are after in this presentation. Now, to study the behavior of the edges, I have to change a little bit the paradigm of the analysis. So here I am performing what we call a supercell analysis. So we take a finite lattice, so finite in the sense that it is finite in this direction. So this is really a free boundary, and this is another free boundary. But the idea is that I have an infinite strip along X. Okay? So that if I consider this strip of cells, which I am boxing, this is my supercell. And it's a collection, a strip of unit cells that spans from free boundary to free boundary. And if I repeat it in space in the direction of the red arrow, it actually reproduces the entire strip. Now I'm going to consider the supercell in isolation. Okay, so I have free end here, and I'm going to impose one-dimensional block conditions in the direction of the arrow. Okay, so I consider it indeed as a periodic unit in this direction. So I perform an analysis very similar to the unit cell analysis that I introduced at the beginning of the presentation, but applied to an entire strip, okay, that contains the ability to model the edges. And if I do that, I come up with these Venn diagrams. So this is a Venn diagram for the entire supercell. So here I have a frequency, just before, like before. And here I have wave number, okay, so the reciprocal of the wavelength for a propagation only in the direction of the arrow. And I see that I have these two interesting modes that appear, these lowest two magenta modes. So first of all, I forgot to mention that all the magenta curves represent modes of the supercell. And for reference, I also place here this kind of black curves, which are modes of the bulk that come straight from unit cell analysis. Now I focus my attention on these two lowest frequency supercell modes. And I'm interested to understand what kind of mechanisms of the supercells they activate. To do that, I'm going to look at the eigenvectors corresponding to the 6 eigenvalues marked by the blue dots. And these are representation of the eigenvector, so the supercell modes. And you see that across the entire set, I observe indeed the localization of deformation at one end, and not only one end, but specifically the end that the polarization vector has deemed as my floppy edge. Okay? So that means that this particular supercell mode is an edge mode. An edge mode means that the deformation mechanisms associated with these modes entail localization or deformation at the floppy edge. And same thing could be said for the second one, although the results would be a little bit dirtier to look at than this one. And that's why I prefer to kind of illustrate the outcome using the first branch. So now let's see if experimentally we can demonstrate this floppy edge mode behavior. So here we are going to perform an experiment. We're exciting the lattice prototype that I showed you before at this frequency. You see that at this frequency, I have the coexistence of some bulk modes, the black branches, and also I have this edge mode, which is the magenta branch. And I'm going to perform the experiment twice. In one case, I'm exciting at the floppy edge, and in the other case, I flip the specimen and I excite at the rigid edge. So this is what happens when I excite at the rigid or non-floppy edge. You see that I excite a long wavelength wave that immediately propagates into the bulk and kind of reaches every region of the domain. So this is a textbook example of a propagation in the bulk that insonifies the entire medium very rapidly. Okay. So the idea, and in contrast, if I excite at the floppy edge, I have very different behavior. You see that my deformation remains at all time instants localized along the floppy edge. The deformation kind of bounces left and right, along this edge, but never really leaks into the bulk. So what is going on here? What's going on is that when I have simultaneous availability of bulk modes and edge modes. However, when I excited the non-floppy side, I do not have the opportunity to activate the edge mode. And therefore, all I see is this bulk mode. While when I excited the floppy edge, I probably excite both bulk waves and edge waves. However, the edge waves are associated with much higher compliance than the bulk ones, and therefore they dominate the response. So the bottom line is that my lattice has an asymmetric wave transport behavior. If I excited at the non-floppy side, I have a conductive behavior in a mechanical sense. So my signal travels through the bulk and reaches the other edge. While if I excite the floppy edge, it behaves like an isolator. So all the signal remains localized close to the source and never really reaches the other end of the domain. And we can also confirm this through some Fourier analysis. So here I'm actually taking the response along the floppy edge, okay? So the time histories of all these points that live on this edge, and I'm performing unit cell analysis, I'm performing Fourier analysis of that data. And so here I have frequency, and here I have wave numbers, and the color in this map represents spectral amplitude. And you see that the response measured along the edge produced this blob, which is this yellow region of high activation. And you see that this blob indeed sits quite precisely on the branch that we had previously computed from the supercell analysis, so the analysis of one strip. Now, the best way to appreciate the non-symmetric behavior, which I just talked about, is by capturing the transmissibility of the domain. So here I'm going to consider the finite lattice, and I'm going to apply the excitation at one end, on one boundary. This is going to be my input port A. And then I'm going to measure the response at the opposite edge. This will be my output port. So it's like a two-port input-output system. Okay? And I'm going to repeat the experiment, exciting both at the non-floppy edge, okay, as well as the floppy edge. Okay, so for excitation at the floppy edge, this would be the red triangle markers. And for an excitation at the non-floppy edge, it would be the blue circles, the blue dots. Now, in this chart that I'm showing, this is the result of our experiments. So every dot and every triangle represents a single experiment performed at a different frequency. Okay? So the reds are excitations prescribed at the floppy edge. The blue are excitations prescribed at the non-floppy edge. And we see something quite interesting. We see that for excitations at the floppy edge, we observe this dip in the response. Okay? So the transmissibility that we compute, which is here defined as a transmissibility of displacement. So the average of the displacement that arrives at the opposite edge divided by the average of the displacement at the edge where the excitation is applied. Now, this transmissibility has a dip, and this dip actually corresponds to the region of existence, the frequency interval of existence of that floppy mode. Meaning that for these frequencies, indeed, our deformation is accumulated close to the excitation point and is not really reaching the other boundary. Interestingly enough, if we excite from the non-floppy edge, we have the opposite behavior. We have a little bit of a peak in the response for those same frequencies, hinting at the fact that here I have a propagation in the bulk that reaches the other edge and then accumulates there. You see, I have this kind of mouth, right? This gap between the two curves, which is a sort of graphical depiction of this asymmetry in behavior. And above a certain frequency, when I don't have these floppy edge modes available anymore, you see that the two curves coalesce. So all asymmetry is lost, and it becomes indifferent at what edge I am exciting. Okay? So I have this asymmetry of behavior, which is available only in this frequency interval, and is completely absorbed and lost at higher frequencies. Okay, one last thing I want to say about this problem. If you appreciated this asymmetry of behavior, so conductive versus isolation behavior, you might be saying, however, I could have obtained this in a simpler, more trivial way. For example, I could have considered a two-material solution, where here, for example, I have a domain that is made of a hard material that is conductive mechanically, and then I could have placed a strip of soft material, like a sponge material, at one boundary. Now, certainly with this configuration, if I excite here, I would observe predominantly localization in the soft layer. And if I excited here, I would probably have propagation through the bulk, and then eventually the signal would reach this layer. So nominally, I would have the same effect that I just showed for our lattice. However, look at what happens here. If I had to somehow lose the soft layer, like strip it out, okay? And this would be something that when we talk about engineering materials is actually of high importance, because we're talking about potential of wear and tear of the material. So whenever we have a material with a skin, we're always concerned with what happens as soon as the skin is removed. Now, if you have to remove this layer, then all of a sudden this edge will become rigid, just like this one. So the asymmetry would be lost, and this will become a trivial piece of hard material. Instead, in our problem, the situation is remarkably different. So let's say that we have this edge which we have deemed to be floppy. And let's say that for some reason we take all this last strip of cells and we take it out. Now this new layer becomes the new edge. And this new edge is still floppy. Essentially, it enjoys the same floppiness properties that this one used to enjoy before. And this is, again, a manifestation of that bulk edge correspondence that we talked about earlier. The floppiness is not an intrinsic property of an edge. It's a property of the bulk that manifests at the edges. Therefore, the bulk endows with this property whatever happens to qualify as an edge at any given point in time. So topology provides a robustness to this problem such that it doesn't even matter what is the particular shape that the edge has. As soon as it is an edge, it's going to enjoy this floppiness, which is given to it, if you wish, by the bulk. So this robustness is really the additional gear, right, that these topological materials have with respect to analogous but more trivial architectures. I'm going to skip this in the interest of time since this is going a little bit slower than I expected. And let me move to the second problem. The first problem was about propagation of waves along edges. This one is instead about propagation of waves along internal interfaces between subdomains. So what we're trying to do is waveguiding. You recall waveguiding from the introduction of the talk, the ability to channel energy along arbitrary paths. But here we want a particular kind of waveguiding, a waveguiding that is immune from backscattering from sharp corners. Now, in order to, one way to achieve this special type of waveguiding is in mechanics, is by creating mechanical analogs of a quantum mechanical effect known as the quantum valley Hall effect. While the theory behind the quantum valley Hall effect is quite complicated, there is actually a pretty bulletproof recipe to achieve this result. And it's a four-step or a four-ingredient recipe. So the ingredients are the following. First of all, I need to start from a lattice whose unit cell feature a six-fold symmetry. Then I need to take the unit cell and somehow I need to break the space inversion symmetry of the unit cell, So that would be the central symmetry. But I need to do that carefully in a way that the threefold symmetry is preserved. And here are a few examples from the literature of how other researchers have done this. This is a result from the group of Massimo Ruzzene, previously at Georgia Tech, now at Colorado. They started from a honeycomb. They were looking at the autoplane vibrations of honeycombs. So the six-fold symmetry of the unit cell comes from the honeycomb shape. And then they placed these magnetic masses at the nodes, and you see that there is an unbalance in these masses between one node and its neighbor, and this is how they broke the space inversion symmetry of the cell. This is an example from the group of Fabio Semperlotti at Purdue. In this case, they used a triangular lattice, which also has six-fold symmetry. And I don't know if you can appreciate that these beams are not straight, but curved. And with this curvature, that's how they broke the space inversion symmetry. And in both cases, then the other ingredients are that I need to now take two lattice domains, let's call them A and B. And this lattice domain features unit cells that are one, the mirror symmetric of the other. Okay? And then I have to make these two subdomains come together to form a domain wall or an interface. And the interface can be a straight line, or it can even be an arbitrarily complex line, provided that we follow some rules. And in fact, you see that these researchers show that, for example, if they created these domain walls or interfaces that are shaped like this, like Z-shaped path, they were able to indeed send waves along this particular path. And more importantly, they were able to show that the wave propagation would be immune from backscattering from these corners. In other words, they were able to observe a very high efficiency of transport for waves that propagate along this path. Now, for all these examples, they were talking about autoplane motion, so autoplane wave propagation. And this is where we come in. Our first objective was to study in-plane mechanics, so look at the in-plane counterpart of this problem. And of course, in-plane mechanics poses some additional challenges, especially from an experimental standpoint, which I will talk about later. But also, we don't want to study only interfaces, but we want to also study junctions. And by junctions, we mean points in the domain where I might have a multitude of interfaces that come together and coalesce. And the idea is to obtain some interesting logic from a mechanical standpoint using these different interfaces and letting them coalesce at junctions. And some of you may be familiar with some similar research along similar lines in the group of Richard Kruster at Imperial College, where they also work with the idea of performing interesting tessellations of lattice domains and working with different junctions. In their case, they were, again, focusing on out-of-plane motion, so flexural waves, while our focus is on in-plane mechanics. Okay, so these are the recipes of our approach. We start from a regular honeycomb, which has this unit cell. Okay? And this is our unit cell. And this is the Venn diagram. The Venn diagram of the regular honeycomb is pretty straightforward. Nothing particularly remarkable to report, except that you see I have this interesting point that I put in a box, which is known as a Dirac cone. Now, the second ingredient is we need to break the space inversion symmetry of the cell. And the way we do that in our problem is by playing with the thickness of the beams. Okay? So you see that in our unit cells, the beams don't have a constant thickness, but they are thicker here in the upper part of the cell, and they are thinner, and therefore thinner in the lower part of the cell. Now, when I introduce the space inversion symmetry, look what happens. This degeneracy is lifted, the Dirac cone goes away, and I open a band gap. Okay, so instead of having this crossing of the branches, I have a band gap. And these 2 points that I left behind are called the valleys of the problem. Finally, I consider now 2 lattices, A and B. So lattice A is like this. The unit cell features the thick beams at the bottom and the thin beams at the top. Lattice B has thick beams at the top and thin beams at the bottom. And now I take these 2 lattices and I bring them together. And I can do that in this fashion where thin and thin come together. I call this a thin interface. And I can do that in this way, which is a thick interface. Now I'm going to consider the lattice, which comprises A and B. And I'm going to look at a supercell again. So it's a strip of the lattice that spans from free boundary to free boundary. And here it has an interface. This is a thin interface, and this is a thick interface. And I'm going to study what is the behavior of this strip, of the supercell. And I end up with this very complicated diagram. Now, you don't want to have to worry about the complexity of this diagram. The only take-home lesson here is that I have some wave modes, so the ability to propagate waves in this region, indicated by the gray background, which is the region where we previously saw the bandgap. Okay? In other words, while a single lattice has bandgap condition in these frequencies, a lattice that involves an interface actually has the ability to propagate waves at those frequencies. And if we look at the eigenvectors of the supercells for frequencies that fall inside this frequency interval, we see that they involve deformation mechanisms that are indeed accumulated at the interfaces. So these waves that we can propagate at those frequencies are waves that are bound to propagate along the interface and not into the bulk, so not far from the domain wall. All right, so I'm going to skip some theory here, and I'm going to show you how this works. I try to be brief because I'm running a little bit long. This is a simulation. We have a domain where I have a domain wall that is Z-shaped, and I have lattice A above and lattice B below. And you see that along the interface, I have indeed 2 thin beams that come together. Okay, so it's very important that I have 2 different types of lattices across the interface. And these are 4 snapshots of the simulation. I see that if I excite at this point, the wave can propagate along the Z-shaped domain, and I can reach quite effectively this point. And I observe no appreciable backscattering from these sharp corners. And in fact, if I monitor what happens at this point with the star, I see that I have this maroon curve that means that the response kind of grows as the wave comes through and then comes back to almost 0 means that the energy actually goes past the corner and very, very little comes back. Very, very little is reflected by the sharp corner. To appreciate how this is different from a trivial configuration, let's look at a trivial bandgap. Here I have the same lattice, but I have lattice A on both sides of the interface. So here I have a path where I am considering all the thin beams, but the important thing is that I have the same lattice type on both sides. And you see that in this particular case, I can also propagate along this path, but unfortunately, I have strong backscattering from this corner. You see that as the wave reaches this corner, a lot of it kind of bounces back, while very little kind of makes it past the corner. And then we were able to confirm this experimentally. This is, again, a slab of ABS material that features, again, lattice A here, lattice B here, and this is my interface. We perform an excitation, exciting with the same setup that I had earlier, and we use a vibrometer to scan the domain. And we were able to capture these scans experimentally, where we see that indeed we are able to propagate our signal past this corner as well as past this corner. Now, of course, here the material has some damping, so I have some attenuation, but I still do not observe appreciable backscattering from the corners. And in fact, if I perform Fourier analysis along this direction, I see that most of my response occurs for waves propagating in the positive direction, which means along the direction of the path. That would be the right side of this domain, and very, very little activation on the left side of this chart, which would represent backscattering. Okay, if I have time just for a couple of slides to finish, I would like to tell you a couple of things about junctions. So here we are considering a scenario like this one, where I have these four interfaces that coalesce at a point. I have three thin interfaces and one thick interface. And I'm asking questions like, if I have a wave that travels along an interface, what happens when I reach the junction? Will the wave want to go one way or the other or come back? Okay. So we spent a lot of time trying to understand what happens when we have these coalescing points, and we came up with a taxonomy of things that can happen. So essentially things that a wave wants to do and things that a wave does not want to do. And for example, we found out that when a wave travels along an interface, it does not want to come back. Also, if it impinges on a junction and then it cannot go straight if we have a transition from a thin interface to a thick interface or vice versa. Okay? Instead, there are things that a wave likes to do. For example, a wave likes to turn sharply if it stays on the same type of interface, or it likes to turn gently if it changes interface from thin to thick or from thick to thin. So in light of this taxonomy of behavior, let's see what happens here. If I excite this situation, this system from the left, my wave will go all the way to this point, and then it will turn back like this. It will now want to keep going straight, but it will turn back. And then part of it will actually turn back this way, so that the energy will actually come back and then live on this edge. So it will never be able to really propagate through the system and reach this other end of the boundary. And these are three snapshots of our simulations that indicate that indeed an excitation that comes in from this side is bound to remain localized at this edge. Okay? And these are three snapshots from our experiment, which confirm the same kind of behavior. Oops. Instead, if I come in from the other edge, I have a very different behavior. The wave comes in along this thick interface, and when it reaches this point, it doesn't want to come back. But instead, it wants to take this route and this route. So the energy will actually split into two parts. And so it will eventually reach this edge. And these are four snapshots of the simulation that indicates that the wave starting from the right indeed comes all the way to the left edge. And these are four snapshots of the experiments, of course, looking a little bit more cumbersome, but confirming the same behavior. So the bottom line is that, once again, we have an asymmetric behavior according to what edge we excite. If we excite from the left, we achieve the behavior of an insulator. because our signal cannot reach the opposite boundary. If we excite from the right, we have the behavior of the conductor, because our signal does reach the opposite edge. Okay? So it's an outcome that is very similar in nature to what I showed earlier for Maxwell lattices, however, based on a different mechanism and available in a different frequency range. So I know I'm out of time, so I'm going to skip the last example, although it would have been cool to look at. And I'm just going to leave on the screen these final remarks, which only really summarize the things that I try to discuss during the talk. So these are the publications that most directly refer to what I talked about today. And I'd like to conclude by acknowledging the support of the National Science Foundation. And again, thanks to Inji Hong and other group members for all the great work. I'm happy that I was able to pull through, although that certainly slowed me down and made my speaking a little bit harder throughout the presentation. Thank you for your attention.
All right, so if you have any questions for Stefano, please raise your hand, and then Mary will unmute you accordingly. Let's open the floor. I have a few questions. So Stefano, if you can go back to your first example of the edge excitation, right? And maybe if you can show the Venn diagram where you're one with the black and orange, slide 17. There's an interesting paradigm. We have been studying excitation by the sources inside the bulk. So here we show that given the frequency, you're going to excite certain modes that are within that frequency. But what we find that is actually equally important is what is the spatial support and variation of the source. In other words, here you have a point source, which is kind of like a delta function in a wave number domains. We cover all the wave numbers. But if you design the spatial support of your source to, let's say, to agree or disagree with the eigenfunction of that mode, then you're going to spread your energy not in the frequency domain, but in a wave number domain.
Yeah, I mean, I guess I can just maybe comment on that. It is true that we always have this duality of problems where we, if you have an initial condition, we impose a spatial profile, so we freeze the wave number or the wavelength, while we look at predominantly at the application that is maybe more of direct engineering interest in experiments where we can only have one or a few excitation points where we impose the frequency, but we do not control the spatial pattern. Right, so in that case, yes, frequency for us is indeed our input variable, and wave numbers follows as predicted by the branches. We have not really looked at these classes of problem in the context of what you're talking about, which is the dual excitation approach. And so I guess I don't have any firsthand evidence of, I guess, confirming whether there would be like a qualitatively different type of behavior. I would assume that if I had to kind of pick a wave number, I should still be able somehow to pinpoint a specific region of the branches that is commensurate with that selection of wavelength. But in terms of, I guess, disappearance of the asymmetry that I talked about here, so the dichotomy between floppy edge and non-floppy edge, I don't have any direct evidence of whether the difference outcomes. I see Baby Vaughn is trying to talk because he's talking to a muted mic.
So may I ask, well, I have a comment if I may.
Yes.
You know, Stefano, the talk was very interesting, but there is, as always, I was claiming you are really a structural engineer, not geotechnical engineer. And the comment that I have is that what you're talking about floppy and rigid, we in structures call it stability or geometric invariance. So yes, you have mechanisms on the floppy side and you don't have it on the rigid side. So that's what it is. It's insufficient connection between the members of the lattice.
Yes, I guess that I don't disagree with the statement, with the reading of the problem through the lens of stability or lack thereof. The thing that is, however, I would say fairly remarkable of this result by Ken Lubensky is the sort of dichotomy of behavior between the two edges, because from the point of view of their connectivity, they are equally connected. So you see here that if I look at this boundary node, for example, as the connectivity landscape is the same, except in terms of availability of links or lack thereof, but is the orientation of them that is controlling the different outcome. So I guess one thing is I guess this element of asymmetry between the edges, which enriches the discussion of that is typically available in the structural engineering literature on the problem. And then the other one is the bulk edge correspondence. So the fact that I have these features of behavior at the edges, which are exquisitely like they're germane, uniquely germane to the unit cell. So in other words, that are not specifically controlled by special properties that are only available on the edges, but are instead robust against little defects and fluctuation in geometry that you may observe on the edges. So yeah, I have not really performed a reading of the problem in terms of the stability analysis, and I don't know if it would provide, it may, additional layers of understanding of this problem. I have to admit that I kind of walked within the pathway of Ken and Lubensky and adopting their framework of interpretation.
Kathy asked a question, and I would like to read it for her because she said her mic doesn't work, Stefano. Or would you like? I'll read it for you, so save your voice a little bit. When you excite the non-floppy side, the wave propagated through the bulk. In that case, when it hits the floppy boundary, it should reflect, and then it seems it would have a local effect. In your study, did you see that interaction with the reflection, or did the wave attenuate before it hit the floppy boundary so you don't see the effect of the reflection?
Yes, we do see an effect of reflection. So what we think happens here, reflection of, let me say, of interaction with the boundary. So what there is definitely, we see some reflection. So actually, it's even hard to appreciate the reflection because it is a fast, extremely long wavelength wave that it kind of immediately insonifies the whole domain. So it almost immediately reaches a standing wave mode, right? So yes, I do see the signature of reflection, which is what immediately produces the standing wave conditions. At the same time, the interaction with the floppy edge, once it's reached by the excitation, is peculiar in that I end up somehow accumulating some deformation at this edge. So once the signal has reached it, it kind of wants to activate that strong deformation. And that is what I think emerges from this plot that puzzled us at the beginning a little bit, but we wrapped our mind around it. That is that when we are at frequencies where that edge is indeed floppy, the excitation that reaches seems to want to accumulate there. So yes, there is some reflection, but part of it is kind of trapped there. And that is why the transmissibility actually happens to have excuse me, a positive peak. So I guess that we see the effect of the reflection that forms a standing wave, but we also activate like a secondary accumulation of energy capability of the output edge. I hope that that addresses the point that was being asked.
I also have one other question, if I may.
Yes.
In your demonstration of the floppiness or rigidity of the edge, in what cases you pushed on the edge? What would happen if you pull on the floppy edge?
So in our case, I don't expect a difference because these are harmonic excitations. So we are indeed pushing and pulling. There would just be a phase difference.
No, but in the static case, just when you pull.
Right. In the static case, it's a good question. I have asked myself that, and I even tried by hand, and I guess that I did not. I don't know if I got to a conclusion that was really maybe satisfactory for me, but I did not see an equivalent localization, so I was not able to appreciate something that was precise.
So this directionality is having to do with the direction of loading as well. Yeah.
In my experience, also playing with the toy, although I want to be careful with I guess proposing a conclusion as firmly as my previous statements that are something that directly related to the angle of our work. But in my playing with the toy, I have certainly felt a experience.
Okay, so
the directionality of the phenomenon.
Okay, so it is different.
Right. It's something that, however, I've not particularly investigated from a static perspective. But you saw that in all my cases, indeed, I was pushing, perhaps slightly, I guess, biased in my observation by similar static experimental demonstrations on different platforms that indeed involved pushing. Okay. Interesting enough, in our problem, which is a dynamic problem, where again, all this idea of rigidity and softness has to be taken with a grain of salt because the meaning of words is relaxed. But here, we emancipate ourselves from that issue because we have a harmonic excitation. So we can conclude that, I guess, if that is indeed a problem associated with the static problem in terms of pulling versus pushing, it does not seem to affect the transportability of the phenomenon to, or at least it seems to be bypassed when we go from statics to dynamics.
Okay. So, Stefano, I think I have a question too.
Yes.
So in the second part of your talk, when you talked about the value Hall effect, you talked about having a specific recipe for designing the metamaterial. And I wanted to go back to the first part with the floppy versus non-floppy edges and see, so are there specific recipes that you can arrive at to actually build these metamaterials that will demonstrate that? I mean, you had one specific case, but I mean, how did you come to that? Did you come to that by trial and error? And then if there is a set of recipes that you have, how might they equate to actual engineering applications that you might want to design one of these floppy, non-floppy edge metamaterials?
Yes, that's a great question because indeed it's something that we discussed with our collaborators fairly recently. Where's the geometry here? So indeed, while there are the mathematics are quite, I guess, convoluted. People have come up with a series of guidelines to design these unit cells where one can expect to have polarization. And essentially, they have to do with the angles that the bonds, now essentially the sides of these triangles, form with respect to one another. Okay. So in general, the more you deviate from situations where these sides are aligned, the more you kind of have a polarization. And for example, here, when you have a situation with isosceles and equilateral triangles, as well as with some tilt, these are two ingredients that are both typically conducive to such a scenario. Okay, because you minimize your chances to have these aligned bonds. So for example, the regular kagome, which is this right here, does not feature that effect. This is a typical example where the bonds are aligned. You would not have it. But interestingly enough, even the twisted kagome lattice, where you don't have this assigned bond, also does not have the polarization if they're both equilateral triangles. So there are a series of ingredients that have been actually put in a taxonomy by our collaborators in the past, but they're not necessarily all intuitive. But there are indeed certain ingredients that one can mix up, knowing that when you have all of them in place, then the polarization is going to be available.
And then I suppose, yeah, and then as a kind of semi-related follow-up question, so are there any cases where these floppy, non-floppy edges appear in kind of natural systems? Like if you think about in some kind of biological system, you can imagine the evolution might have made some kind of animal or organism have behaviors like this to deal with situations they find themselves in the wild. I just off the page question, but I just wondered if there was any.
Yeah, I mean, I've not reflected too much on the biological side of things, and I'm not aware of established research that has tackled that. Although I know that some individuals that are actually thinking about that direction to expand on these ideas. So also. I'm looking forward to see what they come up with. One would say that, one would say, well, why not? I mean, we do have a lot of things that have asymmetry. Well, we have a lot of things that are periodic in nature, and we have a lot of things that have asymmetry. So one would expect to see something like this. The question is, would there be a lot of systems where this periodic structure would kind of say, be available from free edge to free edge, right? Because in order to fully appreciate this phenomenon, you would be able to access it from both sides. Well, I can see like some system having this as skins, right? Where there would be, for example, an exposed edge and an interior edge connected to the bulk. So still, there could be some interesting effects like this, but I don't know if there are any biological system where one would be able to probe equally freely both edges. It seems likely essentially asymmetric cells are conducive to this behavior, and I would bet my money on yes if I have to kind of pick like binarily.
Thanks very much, Stefano.
I had another question or comment from Catherine French. Interesting question that Henrik had on directionality. If the structure deforms on the floppy edge when introducing force, maybe the wave is introducing load when pulling on the structure. And when the structure responds in compliant direction, it cannot transmit load because it is compliant. That directionality of the boundary seems quite interesting.
Yeah, I mean, I think if I understand the question, I wonder if what is being, suggested is maybe that if indeed, like what emerged from Eric's question is that there is a preferred activation of this phenomenon during the pushing phase. Maybe in the dynamics, it is during the pushing phase that we kind of achieve the effect, and then maybe the pulling phase is along for the ride. And sort of just kind of, and I have it like a cycle of pushing every cycle of excitation. I might be kind of reading too much into the question. I'm not sure. My dynamic background discourages me a little bit from in the linear regime. Discourages me from attributing a different physical significance to the pushing and pulling phase of a harmonic load. Nevertheless, the need to kind of reconcile this with Henrik's observation about the static case definitely legitimizes this question. So I guess it...
And conversely, you can also pose the same problem for the stiff edge. If you, instead of pushing it, if you pull it, it may become soft.
No, well, the stiff edge, I think that this demonstration shows that it's not the case, because you see that in this video, I'm going to rerun it. You see that I'm both pushing and pulling.
Okay.
So I guess that if that maybe kind of like eliminates this as a variable from the conversation. And I think I want to say for this one right here is that I just also would like perhaps to try again before really getting to a hard conclusion, because I've really not spent too much time pulling. And I also have to say that when you work with the systems, ideally this would have to be infinitely long in this direction. Working with finite boundaries poses some side effects that are not really part of the theory. And so you kind of have to manage the sides somehow artificially, like I did here, to realize this specimen. And so I want to say that by pulling, the way you engage the sides might contaminate the response. And therefore I might have observed some pinching by pulling, but I might have ascribed it to some side effects that I wasn't quite sure pertained germanely to this theory. So I might have even seen more effective pulling that I recall, but I've not charged it with a lot of significance. So maybe I would prefer to kind of get back to this. I actually have it I brought it home, so I can try it, and then maybe get back to you and Katie with some updates.
And Stefano, one final question. Sorry for too many questions, but what effects would have the length of this specimen? In other words, if it is infinite, it would be the same comparing to the finite in the direction perpendicular to the pushing or pulling.
So into the bulk, right? So yeah. So the effect will be the following in my reading of the problem. So there's a certain attenuation, and the attenuation has to do with the intensity, if you want, of the polarization. So that essentially the deformation decays within a certain number of cells. You can even see it in the eigenvectors, right? Like 2, 3 cells, according to, for example, if it's in a frequency problem, according to the frequency for sure, but also according to just what the polarization, the strength of polarization, we can call it. Now, this is a property that should be independent of the size of the supercell, so essentially how long the strip is. I would say that having a longer supercell would only make you appreciate this better, because if I have an attenuation within a finite number of cells that is not too far from the number of cells that I have in that direction, I might not even appreciate the attenuation very much, right? While instead, if I have a large number of cells in this direction, I still attenuate at the same rate in space. And then I have essentially a large number of cells that experience a zero deformation. Right? So I would say that the only difference in manifestation would be how dramatic the localization would look like.
Okay, thank you.
If I may comment on that, the issue of the evanescent waves in periodic media, its interface, is still wide open, even in mathematics literature. I mean, the question is how does the wave decay perpendicular to the surface? It is likely an exponential decay or a combination of exponentials, but at this point, this is an open question.
Thank you.
We had one, perhaps this could be our final question from Randall Barnes. The maintenance of the one-way transmission, even when the edge is ablated, was compelling. Do you have a comparable engineering, quote, application of the waveguide phenomenon at hand?
Interesting question, because very good question, because it's correct that they fall within a same broad family of problems protected by topology. So there is some kind of immunity from defects and from disturbances in the geometry available in both. However, there's slightly different manifestations. So I guess that the most equivalent thing to the I guess imperfections on the edge of that you saw in the previous problem, that actually that I alluded to in the previous problem, in this problem would be, the existence of disturbances in the geometry along the path of propagation. And so the robustness that I have here is against those kind of imperfections. So for example, if I have a scattering object along the waveguide, I have some protection against the backscattering from it. And the one scatterer that I have used here in my demonstration is the corner. It is the sharp corner, which typically, see, look at this example, does scatter back, while in this case, that in normal cases does scatter back, but with this non-trivial waveguide does not scatter back. So this is the equivalent. This is the kind of geometric anomalies that topology protects the problem against.
All right, I think that's a great place to wrap up. Thanks everybody for coming.
Thank you for staying the whole time, and sorry, the delivery turned out to be a little bit slower than what happens in person. That's just something I just learned.
Very
Thank
nice
you all.
presentation, Stefano.
Thank you.
Get well.
Thanks for the great talk, Stefano.
Thank you.